So dear students, this video is based on the second semester KTU syllabus for mathematics. In this video, we will be discussing about conservative vector fields. Let us begin with the definition of a conservative vector field. A vector field F is said to be conservative if it is the gradient field of some scalar function. That is, we say that a vector field is conservative if there exists a scalar field, say phi, such that F is the gradient of that particular scalar function. That is, F is equal to the gradient of some scalar function phi. Then we say that F is conservative. This scalar function phi is called to be the scalar potential of F, or simply the potential function of F. So if you could find a function phi such that if its gradient is the function F, then we say that the function F is conservative. That is the definition. Now let us move on to the one of the important theorems, that is fundamental theorem of line integrals. This is based on the conservative nature of the vector field F. So let us go through the theorem. Suppose that the vector field f of xy is equal to f of xyi plus g of xyj. If it is conservative, suppose that it is conservative vector field, which means that there exists a scalar function phi with the property that the gradient of that particular scalar function is the vector field f. In some open region D containing the points x0, y0 and x1, y1, and that f of xy and g of xy, that is the component of capital of the vector field f in the direction of the x-axis, that is f of xy, as well as the other component g of xy in the j direction, they are both continuous. If f of xy is equal to gradient of phi, that is there exists a scalar function. So we are taking the assumption that the vector field f is conservative. So f is the gradient of some scalar function, and if we are actually taking a curve C, and C is having the condition that C is a piecewise smooth parametric curve which originates from the point x0, y0 and ends at the point x1, y1 and lies in this particular region D, then this is the conclusion of our particular as a result of this assumptions, we are actually going to conclude this, that is line integral over C f of xy dot dr is equal to phi of x1 y1 minus phi of x0 y0, which means that actually line integral over C f of xy dot dr, this is the work done to move a particle from the point x0 y0 to the point x1 y1 through this particular curve C. That is the meaning of the left side of this equation. This is actually equal to the value of this particular scalar function phi at x1 y1, and from that particular value you have to subtract phi of x0 y0. Or equivalently, we can rewrite this particular equation, this is equation 3, and this equation 3 can be rewritten as f can be replaced with del phi, so that the line integral over C del phi dot dr is equal to phi of x1 y1 minus phi of x0 y0. This is the fundamental theorem of line integrals. In short, what this means is that suppose that you have a conservative vector field, say f, then clearly, since by the definition of the conservative vector field, it is clear that f can be written as a gradient of some certain scalar function, and this particular scalar function is phi. That is, suppose that f is equal to del phi, then if you take any 2 points, say x0 y0 and x1 y1 in a region in which this particular vector field is conservative, then line integral over C f dot dr, you calculate line integral over C f dot dr, this will be equal to the value of this particular function phi at x1 y1, and from that subtract the value of the function phi at x0 y0, which simply says that if you take any curve joining the points x0 y0 and x1 y1, then the work done to move that particular particle from x0 y0 to x1 y1 does not depend on the curve C. It only depends on the value of phi at the endpoints of this particular curve. That is actually what this theorem says. That is, if f is a conservative vector field, then the work done to move a particle from a particular point to another point will not depend on the path joining these 2 points. It only depends on the end points. So it is actually path independent. This is the crux of this particular result. So now let us go to an example. So in this example, the force field F, that is a vector field, F is given to be, F is equal to, F is given as yi plus xj, and it is the gradient of a function is given phi, and the vector field F is the gradient of this particular function xy. That is, you have to verify this. So let us calculate the gradient of phi. So what will be del phi? Del phi is equal to derivative of phi, that is dou phi by dou x, dou phi by dou x I plus dou phi by dou y j. What is dou phi by dou x? Derivative of phi with respect to x, treating y as a constant. So it will be y I plus derivative of phi with respect to y, that is equal to x, so xj. This is nothing but our function f. So this means that this particular force field F is conservative, since we obtained a function phi with the property that the gradient of phi is equal to f. Now to the preceding discussion suggests that the work performed by the field on a particle, so you consider 2 points here. We are actually trying to prove that the work done to move a particle from the point 0 0 to the point 1 1, actually it will not depend on the path, or here what we are considering is that we are trying to find the value of the line integral over C f dot dr, that is work done along different paths. So as a first case, let us take the line segment y equal to x as the curve C. So in this particular case, we have to compute line integral over C f dot dr, and we know that the vector field F is equal to yi plus xj. So if you take y equal to x as our curve joining the points 0 0 and 1 1, then what will be the parametric equation of this particular curve? Y equal to x. If y is equal to x, then r of t will be, we can take x of t and y of t as t. So r of t will be ti plus tj. The point, we have to move from 0 0 to 1 1. So the t varies from 0 to 1, that is 0 less than or equal to t less than or equal to 1. This will be the parametric equation of the curve y is equal to x. Now we have to compute f of r of t, that is f of x of t y of t. F of x of t y of t will be here x of t, here x of t is equal to t and y of t is equal to t. So f of x of t y of t, this is f. So f of x of t y of t will be ti plus tj. Now to calculate the work done, we have to compute r dash of t. So r dash of t, what is r dash of t? R dash of t will be I plus j. Now we have to take the dot product, that is f of x of t y of t z of f of x of t, not z of t, f of x of t y of t dot r dash of t. This will be equal to ti plus tj dot product I plus j. So this will be equal to t plus t, that is 2t. Okay, so now here we have to calculate the line integral over C f dot dr. We know that the integral varies from 0 to 1. So integral 0 to 1 f dot dr, we have computed f of r of t dot r dash of t, that is we have computed it as 2t. So it is equal to integral 0 to 1 2t dt. On integrating, we will be getting integrals 2t square by 2 between the limits 0 and 1, and that is equal to 1. So along the curve y equal to x, what we obtained is that line integral over C f dot dr, the work done to move the particle from the point 0 0 to 1 1 is equal to 1. Now as a next curve, we are going to consider the parabola y equal to x square. Parabola y equal to x square from 0, 0 to 1, 1. So the points are same. Since the curve that we are considering is the parabola, so we have to just change the parametric equation of the curve. So what is the parametric equation of a parabola? Y equal to x square. We have already discussed in our class that if the curve is a parabola, then we can take x of t as t, x of t as t, x of t as t, and y of t as x of t is equal to t and y of t is equal to t square. So the parametric equation r of t will be r of t is equal to ti plus t square j, where t varies from 0 to 1. 0 less than or equal to t less than or equal to 1. Now we have to compute r dash of t. R dash of t. R dash of t is equal to I plus 2t j. Now what is f of x of t y of t? That is f of r of t. F of x of t y of t will be f was we know that f is equal to yi plus xj. So f of x of t y of t means it is equal to y of t I plus x of t j. Y of t I is t square I plus x of t is t j. Next step is to take the dot product of f and r dash. So next step is you have to take the dot product of f and r dash. So f dot r dash. Let us compute f dot r dash. F of x of t y of t dot r dash of t. This is equal to dot product of t square I plus tj and I plus 2tj. So this will be t square plus t into 2t, that is equal to t square plus 2t square, that is this is equal to 3t square. So just look on to this particular step. Line integral over c f dot dr is equal to this has transformed to the integral, normal integral 0 to 1, limit of t is from 0 to 1, and this particular f dot dr, that is equal to 3t square. So integral 0 to 1 3t square dt. On integrating we will be getting 3t cube by 3 between the limit 0 and 1, that is equal to 1. So again we obtain the work done or the value of the line integral to be equal to 1. Now let us consider one more curve. Consider the curve y equal to x cube from 0, 0 to 1, 1. So now let us try to find the value of the same integral from 0, 0 to 1, 1 along this particular curve. So we are actually we have calculated the work done through two curves. Now we are going to calculate the same say the work done to move a particular particle along another curve. So you consider the curve y equal to x cube. So along y equal to x cube, x of t is equal to t, y of t is equal to t cube. Similar to the last problem, r of t will be ti plus, here this is t cube j. Calculating r dash of t will be I plus 3t square j. We have f is equal to yi plus xj. So f of r of t, let me write this as f of x of t, y of t. Can also write it as f of r of t, that is equal to, in fact, y of t I plus x of t j. This is equal to t cube I plus t j. Now the next thing that we have to compute is f of r of t dot r dash of t, r dash of t, that is equal to f of r of t is t cube I plus tj and r dash of t is I plus 3t square. So it will be t cube plus t into 3t square, that is 3t cube. So it will be equal to 4t cube. So line integral over c f dot dr, the work done to move the particle from 0 0 to 1 1 along the curve y equal to x cube. This is given by integral 0 to 1 4t cube dt. On integration again we will be getting 4t raised to 4 by 4 from 0 to 1. Again the value of the integral is equal to 1. So from this example what we understood is that to move a particular particle along this particular conservative field f, the work done along the curve y equal to x, along the curve y equal to x square and along the curve y equal to x cube are all the same. That is, we are obtaining the work done to be same along all these particular curves, which means that the work done does not depend on the curve through which the particle is moved, but only on the endpoints of that particular curve. That is observation that we can make from this particular example. Now let us move on to another example. In this example, the first part is, I think that the first part is quite clear because we have just discussed the same function in example 1. Confirm that the force field f of xy is equal to ya plus xj in this particular example 1 is conservative. We have already shown that phi of xy equal to xy is the scalar field whose gradient is the vector field f. Now here one more thing is asked. Use the fundamental theorem of line integrals to evaluate integral 0 0 to integral 1 1 f dot dr. So here actually what is the question that is asked is that you have to find the work done to move a particle from 0 0 to 1 1 using the fundamental theorem of line integrals. So in fundamental theorem of line integrals, the fundamental theorem of line integrals clearly states that suppose that f is this is the crux of the fundamental theorem of line integrals. The theorem states that suppose that f is a conservative field. If f is a conservative field, then clearly f is equal to del phi for some scalar function phi. Then the work done say between 2 points along the curve C, between 2 points say x0 y0 and x1 y1 along any curve C, this is equal to the value of the function at x1 y1 minus the value of the function phi at x0 y0. So here we are given the points 0 0 and 1 1 and the work done to move a particle from 0 0 to 1 1, this is nothing but phi of 1 1 minus phi of 0 0. So phi of xy is xy, so phi of 1 1 is clearly 1 and phi of 0 0 equal to 0. So 1 minus 0 equal to 0, which actually agrees with our previous result. We have already seen that work done to move this particular particle along any curve, say y equal to x, y equal to x square, or any curve in the universe, the work done to move that particular particle from 0 0 to 1 1 is equal to 1. So this is how to do this particular problem using the fundamental theorem of line integral. So if it is asked like this, you have to calculate this particular function. Either it will be provided or you have to do it with this particular function phi, and you have to find the difference of this particular functions phi evaluated at 1 1 and 0 0, or in general at the endpoints. Hope that it is clear. So now let us move on to another theorem. In this theorem, it states that suppose that f and g are continuous, f and g are components of the vector field capital F, then the following three conditions A, B, C are all equivalent. So equivalent means that you can substitute these by any other statements. In these three statements can be interchanged in any way you like. So the first statement says that f is conservative. So f is a conservative vector field. The second statement states that line integral over C f dot dr equal to 0 for every piecewise smooth closed curve C in D. Let me hold it on. Let us check the third statement. The third statement is just what we have discussed now. Line integral over C f dot dr is independent of of the path from any point P in D to any point Q in D. That is, suppose that you have 2 points P and Q, and suppose that there is any curve. So suppose that there exists suppose that there are 3 curves from P to Q. Then the work done to move a particle from P to Q, that is in fact line integral over C F dot dr. It is independent of the path. So if you take this curve to be C1, this curve to be C2, and this curve to be C3, then the work done to move a particle from P to Q along C1, along C2, along C3 are all equal if F is conservative. And conversely, if there exists a field which has the property that the work done to move a particle from a point to any other point is independent of the path, then that particular force will be conservative. So that is the meaning of equivalence. Now what does the third statement says? The line integral over C F dot dr equal to 0 for every piecewise smooth closed curve C in D. So suppose that you have 2 points P and Q. Then you take a closed curve. You take a closed curve that moves from or you just consider a point and you take a closed curve. So it starts from P and ends at P. Then the work done, if it is conservative, then the work done is equal to 0. This actually follows from the result that suppose that, so F is conservative. If F is conservative, then the work done W, that is line integral over C F dot dr, depends only on the endpoint. Since F is conservative, there exists some function, scalar function. There exists some scalar function phi. There exists some scalar function phi. Since F is conservative, sorry. Since F is conservative, there exists some scalar function phi with the property that F is equal to del phi. So since this particular value depends only on the endpoints, then line integral over C F dot dr will be just suppose that we are considering the point P and the curve is from P to P, then the line integral will depend only on the endpoints, that is the value of the function phi at P, and subtract the value of the function phi at P from that, which means that it will be equal to in fx 0. So in this case the value of this particular integral will be equal to